Trig functions, and again, we're skipping a couple of chapters. I want to get as much trigonometry in as I can because I feel like that's the most applicable thing probably that we do this entire class. Here's what we're covering in this chapter, which, again, the majority of this is going to be reviewed to you. You've seen it before. Right triangle trig and SOHCAHTOA. Measuring angles, sine, cosine, tangent, and their graphs. The other functions, which would be secant, cosecant, and cotangent, and then inverse functions is what you'll be seeing in the chapter. What is trigonometry? Trigonometry is the mathematics of triangles. Everything we'll be doing this chapter revolves around triangles, and actually not just this chapter, but the next 3 chapters is all trigonometry. Your more advanced maths or some of your most basic maths. I know that we went and toured the tech school the other day, and just nearly every one of their labs, whether it be welding, I don't know that they use it very much, but you got your machine shops and all of them, they use trig nearly daily. So many occupations use this triangle or mathematics of triangles, but that's all trigonometry is. Basic trigonometry, SOHCAHTOA. SOHCAHTOA, make sure you know how to spell SOHCAHTOA. SOHCAHTOA is a mnemonic device that reminds us about our trig ratios, our basic trig ratios. Our 3 most basic trig ratios are sine, cosine, and tangent. And these 3 things are ratios. And the reason that it works the way that it does, so if you remember back in geometry, which is actually what we just finished doing in geometry. Back in geometry, we talked about similar triangles. And 2 triangles are similar if they have the same angles. Here, according to angle-angle similarity, these 2 right triangles would be similar. Since triangles, excuse me, or when triangles are similar, their side lengths have the same ratios. Which means, let's say this is a 3, 4, 5 right triangle. This might be a 6, 8, 10 right triangle. But if we're looking at the ratios of the side lengths, like take this angle that I've marked here. The opposite side, the ratio of the opposite side to the adjacent side, 3 to 4. Well, if this is a similar triangle, look at what you've got here, 6 to 8. If you reduce 6 to 8, it's that same 3 to 4 ratio. When you have similar triangles, their side length ratios will always be the same. When we're dealing with trigonometry, we have special names for these ratios. And they are, again, sine, cosine, and tangent. Sine, which is the SOH of SOHCAHTOA, sine is equal to opposite over hypotenuse. It's the ratio of the opposite side to the hypotenuse in a right triangle. Now we need to clear up, just in case anybody doesn't remember, we need to clear up when you're talking about an angle, which one is the opposite, which one is the adjacent, which is the hypotenuse. Hopefully you remember hypotenuse. Hypotenuse in a right triangle is always the side across from the right angle. And all depending on which angle you're talking about, this X, or I'm going to put a Y up here, whether you're talking about angle X or angle Y, you're going to have a different opposite, you're going to have a different adjacent. If you're talking about angle X, opposite is across from. Okay, if this is my angle, it's made by these 2 sides. The opposite side will be the side on the other side. The adjacent simply means next to. The word adjacent anywhere in mathematics means next to. So the only problem is you have 2 sides that's next to angle X. Well, one of them is the hypotenuse though. So the adjacent side would be the other side that is adjacent to angle X. So here's adjacent, here's opposite. Now if you flip over and you start talking about angle Y, let's talk about this angle now. You would have a new opposite and you would have a new adjacent. Hypotenuse would never change. That's always the hypotenuse. So back to our ratio. Sine is always the ratio of the opposite side to the hypotenuse. Cosine is the ratio of adjacent to hypotenuse. And TOA, or tangent, is the ratio of opposite to adjacent. Make sure you know those for your next test. In these chapters, you will start using and seeing a lot of Greek alphabet. 2 of the main ones that we use is alpha and beta. That's not A and B, but alpha, beta. This is a lowercase alpha, and if I'm not mistaken, well, actually, I say lowercase. That might actually be your capital alpha and capital beta. I'd have to look it up. I don't know. But the same way in our letter system, they have capital letters, and you don't have to know that though. But alpha, beta, and gamma are the three ones that we use most in this chapter. And you see there alpha, beta, and then you'll have gamma, which looks kind of like that, kind of like a Y-looking thing. Does anybody know what comes after alpha, beta, gamma in the Greek alphabet? I don't know why anybody would know that, but anybody? Delta. You're exactly right. And we talked about delta earlier this year. Alpha, beta, gamma, delta, epsilon, and I have no idea what comes after that. But I did have a college professor that made us memorize. I think you said you did too. I had a college professor that made us memorize the Greek alphabet. But anyway, alpha, beta, it says sine, cosine, tangent. Find the exact values of sine alpha, cosine alpha, tangent alpha, sine beta. So this is just our basic trig here. Sine is the ratio of opposite over hypotenuse. And if you always want to start out with SOHCAHTOA, just so you can remember, SOHCAHTOA. To find the sine of alpha, sine is the ratio of opposite to hypotenuse. So we find alpha, and we find the opposite side and the hypotenuse. Brett, what side would be opposite of alpha? And are we given the hypotenuse? No. Does anybody remember how to find the hypotenuse? Hopefully. Pythagorean theorem. Yeah. A squared plus B squared equals C squared. So that is another tool that you'll need for this chapter. A squared plus B squared equals C squared, since you're dealing with right triangles. Something else you might need to know, I'll go ahead and put it, the three angles in any triangle is always equal to 180 degrees. So that's a couple of things you need to keep in your toolbox for the chapter. So you have 4 squared plus 8 squared equals C squared. To get rid of a square, if you want to, I go ahead and square out the whole side. So you have the square root of 4 squared plus 8 squared, which is 16. 64, that's the square root of 80. Which can be split into root 16 times root 5, which is 4. Oh, it's acting crazy. 4 root 5. 4 root 5. So now, sine of alpha is 4 over 4 root 5. Let's clean that up. And that's really the only thing that makes these problems hard is remembering how to clean it up. Well, first off, 4 and 4 cancel. And I have 1 over root 5. We cannot leave a radical on the bottom. You cannot leave a radical on bottom. So to get that radical off bottom, just a reminder, we're going to multiply top and bottom by root 5. 1 times root 5 is root 5. And root 5 times root 5 is. So therefore, again, sine of alpha would be, there we go, root 5 over 5. Cosine alpha. Cosine is the ratio of adjacent over hypotenuse. So, Avery, find alpha. What is adjacent to alpha? Thank you. And what is the hypotenuse once again? And 8 and 4 will reduce to 2 over 1. So you have 2 over root 5, and hopefully you're going to do this so much that you're going to get used to when you multiply top and bottom by root 5, you're going to see what happens. 2 times root 5 will not combine, so it stays 2 root 5, and root 5 times root 5 is simply 5. So for cosine alpha, you get 2 root 5 over 5. Tangent. I like tangent. It's going to be a little bit easier on this one. Tangent, Abby, is opposite over adjacent, which reduces to? Over 4, which reduces to half, right? Okay. Now all of our betas. Let's start with sine beta. And the only thing is you have a different opposite and adjacent here. Elizabeth, what is opposite of beta? And hypotenuse, I erased, but what was hypotenuse? 4 root 5, okay. So you have 8 over 4 root 5, which reduces to 2 over root 5, which is 2 root 5 over 5, which should look familiar. Do we have to go through that whole process again? No. Since your opposite adjacent simply flipped when you went from alpha to beta, 2 root 5 over 5, was that not the, what was it, the cosine of alpha, right? So would the sine of alpha not be the exact same thing as the cosine of beta, right? Or excuse me, we're doing sine, cosine beta. Let me rewind that. So should the cosine of beta not be the same thing as the sine of alpha? Yes. Cosine of beta, here's beta. Cosine is adjacent over hypotenuse, so it's just 4 over 4 root 5, which is going to be that same root 5 over 5. And the tangent of beta, tangent is opposite over adjacent, which instead of 4 over 8 is now 8 over 4, which is, instead of a half, is now 2. So there are relationships there. Sine of alpha, cosine of beta are going to be the same. Cosine of alpha and sine of beta are going to be the same. The tangent of alpha and the tangent of beta, since you're going from opposite over adjacent to adjacent over opposite, the tangent of alpha and tangent of beta will simply be reciprocals of each other. Common, these aren't common, sine, cosine, and tangent of angles. Now we're doing this 2 different ways, and then we're going to put the 2 together. But to find the cosine of 87, this is going to require calculators. Back in the olden days when I took math, we used tables. Y'all are fortunate. You can type it straight into a calculator. That was in high school. Now in college we use calculators. But just to show you how to do this, and just to remind you of something. When you first pull up your calculator, and you need to know what the cosine of 87 is, I just want to remind you, you're actually looking for, if I have an 87 degree angle, what would be the ratio of adjacent to hypotenuse? That's what your calculator is about to give you. For all 87 degree angles, whether it be a small triangle or a bigger triangle, the angles don't determine size of the triangle, because we know 2 triangles that are similar could also have a small triangle with an 87 and a big triangle with an 87. But you're actually finding the ratio of adjacent to hypotenuse for a triangle with an 87. Cosine 87, enter. That's all you got to do. Some of you got a different answer from what I just typed in. Here's why. Make sure this is an 87 degree angle. This is not an 87 radian angle. So what you got to do, hit your mode button and just make sure you're not in radian mode, but you are in degree mode. We will be constantly flipping back and forth between radian and degrees all through this chapter. Radians are simply another way of measuring angles. We've measured degrees our whole life, but now we're going to deal with some radians in this chapter. So that's how, if it's talking about radians, that's how you would get to it. But since we're discussing degrees, I'm good there. So usually you round these things to about 4 decimals, so about 0.0523. Sine of 24, same thing. Here's your sine button, 24, enter. I'm in degrees, so I'm good, 0.4067. And I think we're good with that. You can try to type in the third if you would like. This is the whole purpose of what we just showed you. Keep in mind that sine, cosine, and tangent are ratios of side lengths. We can find those ratios by using our calculator and figure out what missing sides are. And that's what we've got here. You're given that angle alpha. You're given a right triangle, and what we're doing today only works for right triangles. And you're given that alpha is equal to 60 degrees. You're given that C, well, I don't know which one C is. Here's what you got to remember. Angle alpha will always be across from side A. Angle beta will always be across from side B because it's like B and B. Angle gamma will always be across from side C, and C will always be your hypotenuse. A, B, and C, or A and B are your legs, C is your hypotenuse. So if we're given this information and we want to find side A, this is our side A because it's across from alpha. A and alpha are opposites, okay? How do we find that missing side length? By using our basic trig ratios. Step number 1, and again, when I start my homework, I would just keep this on the side of my paper so I don't have to keep writing it over and over and over. SOHCAHTOA. Step number 1, determine what type of problem you have here. Do I have a sine problem, do I have a cosine problem, or do I have a tangent problem? And here's how you determine that. You're given this angle. Well, first off, these O's, H's, and A's have absolutely nothing to do with angles. They're dealing with the side lengths. If given a 60-degree angle, this would be my opposite side, and since this is across from the right angle, this is the hypotenuse. I'm dealing with the opposite and the hypotenuse. Now, why is this so confusing on this problem? Because I called it A. That is not the adjacent side. That is not the same as this A. This A stands for adjacent. This A does not stand for adjacent because obviously that is not the adjacent side. This is. So you're dealing with the opposite side and you're dealing with the hypotenuse. Opposite and hypotenuse, I see there O and H, is a sine problem. The sine of an angle is equal to opposite over hypotenuse. That's your equation. The sine of an angle, we're given the angle here. The sine of alpha is equal to opposite over hypotenuse. Alpha is 60. The sine of 60 is equal to opposite over hypotenuse. That is a one-step equation is all you've got, all you're left with here. From the previous examples, anytime you see sine of 24, cosine of 87, tangent of something, that's a number. Cosine of 87 was that number. Sine of 24 was that number. The sine of 60 is a certain number. Type that in your calculator. What do you get? Sine 60? 0.8660. Do you see now it's a little one-step equation? To get rid of the 20, we're going to come over here and multiply by 20. You're done. And A is equal to about 16 point something. So we'll call it 17.3. Done. So that's what trig does for you. Trig allows you to take two pieces of any right triangle and actually find any other piece that you need. Okay, next problem. Beta is 45 degrees. We'll call this beta. Beta is 45 degrees. Somebody tell me what the other angle would be. 45 degrees. This is actually, we're going to get into special right triangles. This is another one of your special right triangles. The previous problem was as well. So beta is 45. This would be B. This would be C, which is 10. And this would be A, which we'll call it A. So there's the information you're given. You're given beta is 45. You're not given side B, which would be across from it, but you are given side A. Or no, you're actually finding side A, but you're given side C, which is the hypotenuse. Noah, I need to know if this is a sine, cosine, or tangent problem. Sakatoa. Am I dealing with opposite over hypotenuse, adjacent and hypotenuse, or opposite and adjacent here? Adjacent and hypotenuse, good. That's a cosine problem. So you always set it up, cosine of the angle, Tootin, help me do that. The cosine of my angle, which is equal to, perfect. And I'll go ahead and tell you, just so I can type it all in at once, here's what I do. I go ahead and get A by itself now. Division by 10, mark it out, come over here, do times 10. On your ACT, once again, since on your ACT you are not required to use a calculator, they would leave their answer somewhat like that. On this problem, they would clean it up, and I'm going to show you here in a few slides later how you could clean that up without a calculator. So you have 10 times cosine of 45, which is, well, don't do 10 times something. Go ahead and type the whole thing in. 10 times cosine of 45, what do you get? So we'll call it 7.1. So A is about 7.1. See how much you remember about geometry. What's the other side length? Without using anything? 7.1. That's an isosceles triangle. Why do we know it's isosceles? Well, if this is 45 and this was 45, you have two equal angles, you have two equal sides. In a 45, 45, 90, the two sides will always be the same as well. So the other side would also be 7.1. And it should make sense, I'm coming back to it. It should make sense. Why? Because if I'm looking to solve for this, let's say this is 45 degrees, and what if this was your new x, was this side? You would do the cosine of 45 is equal to adjacent, which is now your x over 10. It's the same problem, identical. Okay, next one. I'll let you set this one up. Okay, here's a picture drawn of this relationship. Alpha 32.4, we don't have anything about side A, which is across from it. We do know that B is 10, which is your other leg on this right triangle, and we're looking for C. Logan, given this information, sine, cosine, or tangent, this looking for or dealing with these two pieces, which one are you going to use? Good. Because this is adjacent, which is 10, and this is hypotenuse, which is C. Now, this problem is a little bit different. And we covered some of these in geometry, but I want to remind you on how to do it. Some of you put C over 10. That's wrong. Okay? The variable does not always go on top. When you're dealing with cosine, it's always adjacent on top, hypotenuse on bottom. It's the ratio of adjacent to hypotenuse, not hypotenuse to adjacent. So, again, always put your adjacent side on top. So what do I do when I have the C on bottom? Here's your steps, and honestly, you're to the age now to where you can probably see this just as well as the shortcut. Imagine doing this. When C's on bottom, take and move C to the other side. How are you going to move C to the other side? Through multiplication. Now that C's on the left side, I need to get it by itself. You cannot isolate C where it's at. You cannot move the 10 over to the other side and isolate it because it's not by itself. It has a fraction mark and it has a 1 on top. It's still not by itself. I need just plain C. And the best way of doing that is what I said. Move the C over here and then take this cosine stuff, and in the same step, now move it to the other side. How do you move cosine over now? Divide it. So you're going to take C, move it over here, and then move cosine pretty much in its place. So to get your final answer, you're going to do 10 divided by the cosine of 32.4. If you didn't understand that, here's the other way of looking at it. Here's how we did it in geometry. I put a 1 underneath it. Now you can solve it like a proportion. Now it's a proportion because you have a fraction that's equal to a fraction. How do you solve proportions? The shortcut is the two numbers that are across from each other, 1 and 10, you multiply those, and then you divide by what's left. You get the same answer, 10 divided by cosine 32.4. When you type that into your calculator, you get C is equal to, or about, somebody got it? 11.8. Now, if you did it wrong, I'll show you a way that you can always catch your answer if you'll check this after you're done, and it'll tell you whether or not you did it right or wrong. If for some reason you accidentally typed in 10 times cosine 32.4, you're going to get a number smaller than 10, because cosine of 32.4 is about 0.7. So you multiply 10 by something close to 0.7, you're going to get about 7 as an answer if you do it that way. Could this be 7? Absolutely not. There's no way. This is the hypotenuse. The hypotenuse has to be the longest side. So on your test will be multiple choice. What I would do to begin with, go through, and if you're looking for a hypotenuse, mark out all the ones that are smaller than the legs, because you know that can't be the right answer. Okay, moving on. Another one of these. I must like these problems. We've done plenty. Alpha is 20 degrees. You're given A is 15, and we're looking for B. We haven't worked any tangent problems. That's the reason I threw this one in. This is a tangent problem. Because we're dealing with opposite and we're dealing with adjacent. The tangent of 20 degrees is equal to opposite over adjacent. We have another one where the variable's on bottom. So move the variable to the left, move tangent of 20 to the right, and you get 15 divided by tan 20, which is how the ACT would leave your answer. Done. But when you actually type in 15 divided by tan 20, Jordan, type that in and see what you get. I'm guessing a number bigger than 15, just because, here's my thought, as Jordan's typing that in. This is 70 degrees. Let's go back and revisit geometry and remind you that when you're dealing with a triangle, the smallest angle will always be across on the smallest side. The biggest angle will always be across on the biggest side, which is the reason the hypotenuse is always the biggest side. This 70-degree angle is going to be a whole lot bigger, or create a side a whole lot bigger than the 20-degree angle. So, Jordan, what'd you get for that? 41.2. So you see how much bigger that was? And it was because of that bigger 70-degree angle across from it. That is not drawn to scale. I just drew a triangle there. Now let's work these problems backwards. Above the sine, cosine, and tangent buttons on your calculator, and you will definitely need a scientific calculator for this. But above sine, cosine, and tangent, you have sine with a little -1, cosine with a little -1, And we know that those are inverses because we've dealt with inverses this entire time, like f inverse. Okay, that's what the little negative one means. So we have inverse sine, inverse cosine, and inverse tangent is what it's called. Here's what you use inverses for. Let's go back to 7th grade real quick. X plus 3 equals 5. How do you move negative or positive 3 to, or plus 3 to the other side of the equal sign? You subtract 3, right? Why do I subtract 3 when you have plus 3? Because those two things are inverses. Why do I, when I have x squared equals 4, why do I come to the other side and take the square root? Because those two things are inverses. If I had 3x equals 9, why do I go to the other side and divide by 3? Because those two things are inverses. So if I have an equation that looks like this, how do I take a cosine from one side and move it to the other side? I do the inverse cosine. To get x by itself, if you need to move a sine, cosine, or tangent function to the other side to isolate x, to get it by itself, you will simply perform the inverse of that on the other side. So you have the cosine of x equals 0.5. To get rid of cosine, you're going to go to the other side and you would type it in as the inverse cosine, notice the little negative 1, inverse cosine of 0.5, enter. You get 60. What you just did was ask your calculator the cosine of what angle is 0.5. And you can type that in and check it. The cosine of 60 is 0.5. If you could use trial and error there. Cosine of what angle is 0.5. You can start trying to plug in stuff. And I don't know how deep you got into trig in algebra 2, but do this for me. Type in the cosine of 300. What do you get? So you know what happened? Your calculator just lied to you. Because it said the cosine of 60 was 0.5, which that is true, but unfortunately that's not the only answer. And that's where we're headed with this is this equation. Cosine of something equals 0.5. You know how many answers that has? Millions and millions of answers. That's not the only one. Okay, 60 degrees, 300 degrees, 660 would be a solution there. 1,020 would be a solution. But obviously, if I can do it in my head, it's pretty easy to find the other solutions once you have your originals. Sine of something is 0.2974. I'll give you just a second. I need to get rid of the sine. Get rid of the sin out of your life. I need to get rid of the sine by moving it to the other side. I'll give you a second to try that on your own. So move it over, and we're going to type in, and again, ACT would just simply leave this as this. X equals inverse sine of 0.2974, which is about, how many degrees? So about 17 degrees. And they'll tell you, do I round it to the nearest degree, do I round it to the nearest tenth, or what? So X is about 17 degrees, or, and I'm not telling you how yet to get these, but X could also be 163 degrees. That'd be another solution to this, but we'll talk about that later. Tangent of X is, and let's not even type this in, just to show you. The solution would be the inverse tangent of root 3. To get rid of a tangent, simply do the inverse tangent. That's enough of that. Here's what you're going to use those for. Okay, now that we know how to find inverse sine, inverse cosine, inverse tangent, here's why you do it. Finding missing angles. You're given side lengths, and hopefully you can see the application in this. From here on out, if you have a triangle and you have two sides, or right triangle right now, we'll apply this to your other triangles later. But if you have a right triangle and you're missing, or you've got two sides, well, you know the third side because of Pythagorean theorem. And from what we're doing now with trig, you know every angle inside that triangle. So you can use the information you're given to find any missing information. Here's how you do it. If we're looking for angle A, 4 is opposite, 8 is adjacent. We're starting out with the exact same method. Am I using sine, am I using cosine, or am I using tangent? In this case, it would be, good, tangent. The tangent of your angle, we're not given an angle now. You're looking for an angle, so the angle is your unknown. So the tangent of my angle is equal to, help me finish this, Daniel, opposite over adjacent, which would be, do I need to reduce 4 over 8? No, because you're simply going to be using that to find your answer. If you want to, if you're OCD about it and would like to put a half there, that's fine, but it's pointless. That has absolutely no impact on your answer. Here's why. It all goes back to that similarity stuff. If you were dealing with that triangle and I asked you to find alpha, you would do it the exact same way. Why? Because these two triangles are similar. The reason I know those are similar is by side angle side, which you also did in geometry. Man, that's been a while. I don't remember any of that stuff. That's fine. That's fine. You probably won't use it after you get out of high school anyway. So tangent of alpha equals 4/8. Let's take tangent. Let's move it to the other side. The way we move tangent to the other side is by doing the inverse tangent of 4 over 8. Now ACT here, yeah, I would leave it as inverse tangent of 1/2. Okay, but you don't have to reduce that because you're simply typing it into your calculator. Inverse tangent of 4 over 8. Make sure you're in degree mode because I really want my angle in degrees because I don't understand radians. So that means that alpha is about, Carly, what'd you get for that one? So we call it about 27 degrees. And then you can go a step further if I ask you to. I didn't on this, but you could go a step further, and if I say find all the angles, don't go through that process again. Now use your basic geometry. Since this is 27, this is 90, the 3 have to add up to 180. I think that leaves you with 63 degrees. So that's the easy way to find your other angle. So let's find beta. Here's beta. This would be the hypotenuse. Identify it first. It's across from the right angle. So we know we're either using sine or cosine because they're the ones that deal with hypotenuse. And you also have the adjacent side there, which is 8. Savannah, since I'm dealing with adjacent and hypotenuse, what ratio am I going to use? Good. And the cosine of my angle, this is your equation. Always just set up the equation to begin with. The cosine of my angle is equal to adjacent over hypotenuse. There's no sense in reducing it. Because you're about to, in order to isolate B, you're going to move the cosine to the other side by simply doing the inverse cosine. And you're going to type it in as the inverse cosine of 8/12. Colby, once you get that, please tell me what you get. 48.2 degrees, which we'll call 48 degrees. You can subtract from 180, that gives you 42 degrees. If I did ask you for this, if you needed the third side, we've already done that once, but you'd use Pythagorean theorem. Okay. Or you could use one of these angles and sine, cosine, and tangent to find the other side. That's not a good version, or not a good way of finding it because you're using a rounded answer. This is a rounded answer, and it's really a bad idea to use a rounded answer to find another answer. So Pythagorean theorem would work much better there. If I ask you to solve a triangle, now we're putting it all together. Find everything is all I'm asking you to do here. So you're given one side length is 31, the hypotenuse is 42. We don't have the other side length. Well, let's find the angles first. Because I can very easily find the angles with what I'm given. It doesn't matter which one you start with. If you want to find angle A, let's talk about your two methods here. Allie, if I want to find angle A, okay, I'm given this side and the hypotenuse. Is this opposite or adjacent? Opposite or adjacent, Allie? Good, so that would be a sine problem. So the sine of A equals opposite over adjacent. That's one way to solve for it. What if I want to find B first? Help me with it, Anna Marie. If I wanted to find B, this is the hypotenuse, but 31 now, is it opposite or adjacent? If I'm looking for B, adjacent. So that'd be a cosine problem. So that'd be the cosine of B is 31 over 42. Go back to what I told you at the very beginning. Isn't the cosine of one angle the same thing as the sine of the other angle? Is this not the exact same problem? Sure. Lydia solved this one for me. The sine of A is 31 over 42. Move this over by doing inverse sine, and at the exact same time, Brianna solved this one for me. Take the cosine, move it over by doing inverse cosine. Lydia, what do you get for A? About 48. And really, we don't have to do what Brianna's doing now. Because could we not just take that and, okay, if this is 48 degrees now, the 3 add up to 180, and we're going to subtract them, and Brianna, what are we going to get for B? And get the exact same answer. You can do it either way. Okay, that makes sense. So whichever method you prefer. Now we're missing, by saying solve the triangle, again, I mean find everything. We've got the 3 angles, we've got 2 of the sides. So to find the other side, again, Pythagorean theorem, 31 squared plus, we'll call it x, equals 42 squared. Now let me show you a trick on this. To type this into your calculator, let's save some time. To type this straight into your calculator, here's your steps. And before you even square it out, move that over. So you now have x squared equals 42 squared minus 31 squared. And to get rid of square, just square root the whole thing. That's what I would type into my calculator, just where I can type it in all at once. Subtract the other term, take the square root to get rid of a square, and you get, anybody, about 28.3. So you've solved the triangle. There's all the missing pieces. Okay, that's what I mean by that. Okay, next up, the other 3. Cosecant, secant, and cotangent. The other 3 trig ratios. Cosecant is simply the, don't say inverse, but reciprocal. And catch me because I'm horrible, bless you. I'm horrible about saying that. I'll say that cosecant and sine are inverses of each other. They're not. They're reciprocals of each other. Because cosecant, look what cosecant is. Cosecant, instead of opposite over hypotenuse, is hypotenuse over opposite. Secant is the reciprocal of cosine, which is hypotenuse over adjacent. Cotangent is simply the reciprocal of tangent, which is adjacent over opposite. So really, do you have to learn new stuff here? No, just learn which ones go with which ones. Because sine is opposite over hypotenuse. If you know that cosecant is a reciprocal of that, then you know what it is. Secant and cosine, cotangent and tangent. Here's how I remember this. Sine goes with, and here's the abbreviation, cosecant. Cosine goes with secant. Now the tangent one's pretty easy. Tangent goes with cotangent. And the tangent-cotangent relationship kind of gives me a way to remember these. Tangent, cotangent, sine, cosecant, cosine, secant. Prefix co. What's co mean? All you English buffs out there. Give me a 1 or 2 word definition for co. 2 things that are together. That'd be a good word, together. Co-workers, cohorts, 2 things together, right? Sine, cosecant, cosine, secant, tangent, cotangent. So you've got your basic 3, sine, cosine, and tangent. And then you have these other cos that go with or together with that other corresponding. So if you can't remember, you might be asking yourself now, is it cosine and cosecant that go together? No, because that's 2 cos together. Okay, you're going to have a sine and a cosecant. You're going to have a cosine with a regular secant, and then tangent with cotangent. So co meaning with or together, that it's going to be with one of the other functions, okay, without a co. That's how I have to remember it. Now, how do we type these in? Secant of 1.325, your calculator does not have a secant button, a cosecant button, or a cotangent button. So here's what you have to do. Secant is the reciprocal, okay, cosine, right? Secant goes with cosine. Secant and cosine are reciprocals of each other. Cosine is adjacent over hypotenuse, and secant is hypotenuse over adjacent. So what you can do to find these is, in order to find secant of 1.325, type in the cosine of 1 over 1.325. excuse me, let's rewind. 1 over cosine of 1.325, which will probably also give you an error or a funny answer. Let me explain something. I hate that I gave you this problem already. Notice something about this 24 right here has a little degree symbol. This is not degrees. And we're going to talk about radians later on, but let me go ahead and share with you, if it doesn't have a degree symbol, it's understood to be radians. So in order to type this in, you actually have to go back to radian mode, and I can type it in up here for everybody if you don't want to do this. So to find the secant of something, that would be 1 divided by the cosine of that same thing, 1.325. And you should get about 4.10. My bad. I threw out a radian problem. Now the second one, cosecant. Cosecant is a reciprocal of sine. So to find the cosecant of 24, that would be 1 over the sine of 24. And I put my 1 over while I go in the wrong spot as well. That's the reason I wanted to rework those. 1 over the sine of 24, or the reciprocal of the sine. And we get, anybody get it? That way I won't have to work it. About 2.45. Sounds good. Any questions on how to type those in? That's all they are. There's reciprocals. And honestly, I'm not going to lie to you, you don't use secant, cosecant, and cotangent a lot. I tell you, it becomes weird when you get into calculus. Because then all of a sudden, they start coming out of nowhere. It's like, where did that come from? So they start appearing, and that's the reason really we have to go over them, because we use them a good bit in calculus, but not near as much in pre-calculus. I like to introduce them. So that's enough of them. But I can tell you this, cotangent, to type it in, you simply do 1 over tangent of that. By the way, that's pi. To find cosecant of that, you do 1 over sine of that. Okay, because sine and cosecant are simply reciprocals of each other. That's enough of that. Okay, maybe 1 or 2 more problems, then we're done. Find all 6 functions of alpha and beta. This will take forever. You got 12 different answers here. You got to find the sine, cosine, tangent, secant, cosecant, cotangent of alpha, and the exact same thing of beta. So here we go. Like I said, this will take just a little while. Sine of alpha, and I'll fly through it as quick as possible, is opposite over hypotenuse. Because really, I'm interested in you knowing how to do it, but I'll show you where you're going to have issues. It's probably the reduction part. 2 divided by 2, that cancels. Root 3 over root 7, you can't have a root on bottom, so let's multiply top and bottom by root 7. Gives you root 21 over 7. That's the part I'm really interested in, is knowing, being able to rationalize is the word, rationalize that denominator. Cosine alpha. Cosine is adjacent over hypotenuse, which would be 4 over 2 root 7. 4 over 2 reduces to 2. 2 over root 7, multiply top and bottom by root 7, gives you 2 root 7 over 7. Third one, tan alpha. Tangent is opposite over adjacent, which is 2 root 3 over 4. That's nice. No radicals on the bottom. 2 over 4 reduces to 2, so that would be root 3 over 2. Let's go to cosecant of alpha. And the reason I'm going to do cosecant first is, since I did sine, cosine, tangent, I know cosecant is reciprocal of sine, then I'll do secant, which is reciprocal cosine, and these won't take as long as you would think. Cosecant is the reciprocal of this. So really all you've got to do is just flip this. But even better than that, I'd go back and I'd flip it here. And I'll show you why in just a second. So you had before 2 root 3 over 2 root 7. Now you'll have 2 root 7 over 2 root 3, which we already know the 2's will cancel. So that'd be root 7 over root 3. Multiply top and bottom by root 3 would be root 21 over 3. And you could go back over here and just go through the process again. Again, cosecant, hypotenuse over opposite. Secant of alpha. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. Therefore, secant would be hypotenuse over adjacent. Now, that's kind of cool. You see now why I'm telling you flip it from there? Because then you get root 7 over 2, and you don't have to rationalize it. To where if you'd have flipped your answer, you got 7 over 2 root 7, you'd have to multiply top and bottom by root 7, just ugly. Okay? So flip the first answer, then you don't have to deal with it. And then cotangent, instead of root 3 over 2, you have 2 over root 3. Now that one you do have to rationalize, that'd be 2 root 3 over 3. Multiply top and bottom by root 3. Here we go. Sine of beta. And yes, I'm going to use the shortcut because a lot of people are thinking, now, couldn't you just, right? Yeah. Sine of beta is, here's beta now. Sine is opposite over hypotenuse. So 4 over 2 root 7, wait a minute, isn't that what we did here? So is this not the answer to sine of beta? Cosine of beta, would that not just simply be the same as this? Tangent of beta, or would it be the same thing as? Say it again. Tangent of beta, it would be the same thing as cotangent of alpha. Now you're starting to, we're going to get into some, what's called identities. You're starting to see some of these identities yourself. The tangent of beta, okay, here's beta. Tangent would be opposite over adjacent. So 4 over 2 root 3, hey, this was 4 over 2 root 3 right here, wasn't it? And I'm not going to go through the rest of them, but you see the process. If you don't want to do that, that's fine. Tangent of beta is opposite over adjacent. Do 4 over 2 root 3. Reduce that, you get 2 over root 3. Multiply top and bottom by root 3, you get 2 root 3 over 3. Same answer. Okay? If you want to go through the process again, that's perfectly fine with me. Okay. These problems right here are on the ACTs every time. Okay? Nearly everyone ACT practice test that I've seen has one of these on it. To where they'll give you one sine, cosine, or tangent, and they'll ask you to find another one. These are so easy. Okay? And they're usually one of those last 5 problems that people have issues with. Sine of beta is 3/5. And we're asked to find all 5 of the other. Now, they're not going to do that. They're going to say, okay, here's sine of beta. You find the tangent of beta. Or here's sine, and you find the cosine. Here's one method. And probably the easiest method here. Let's say this is beta. If the sine of beta is 3/5, remind me, Caleb Haynes, SOHCAHTOA, SOHCAH2OA, sine is equal to what over what? Perfect. Guys, look. Sine is opposite over hypotenuse. That's what they're giving you. So if the sine of beta is 3/5, then that means the opposite side would be 3, and the hypotenuse would be 5. That makes sense. So how do you find the other missing side? Pythagorean theorem. Does anybody know that's actually a triple? 3, and then a 3, 4, 5 right triangle? Correct? So now do you have cosine, you have tangent, you have all of them. Because pretty much all you're having to do on these is draw your triangle. And that's what we have now. So cosine would be 4/5. Tangent would be 3/4. Secant, let's see, I'd have to write them down. Secant, cosecant, and cotangent of beta. Let's see, secant would be the opposite of cosine. Cosine was 4/5, so secant would be 5/4. Cosecant would be 5/3. Cotangent, let's see, tangent was opposite over adjacent, so cotangent would be the opposite of that, 4/3. That's how you'd find the others. Or, you can write these down. These are your first identities. Normally I don't give you these till later, but just for shortcut reasons, you can write those down. These are 3 rules, 3 identities that once we get deep into trig, you will use a lot. So you might want to put it somewhere to where you can find these. The last one, I don't know if y'all remember Miss Niblett or not. Miss Niblett was my Math 113, the same class. She was my Math 113 teacher at Northeast. She always joked that she's going to have the Pythagorean identity there. Sine squared plus cosine squared equals 1. She's going to have it tattooed on her because she enjoyed it so much. But tangent is equal to sine over cosine. Cotangent is cosine over sine. And that should make sense. If tangent and cotangent are reciprocals, then, yeah, that's why. And then sine squared plus cosine squared equals 1, probably the most famous of the identities of trigonometry, which is actually what we're going to use here. Well, we'll pick up there tomorrow after you get those written down.